Hello everyone. In this session, we will understand about 8086 CPU architecture more in detail. That is, in addition to the CPU architecture, in this session, we will also have an introduction to the memory. That is, the memory that is going to be used in 8086. Let us get into the details. If you can have a look at the screen, the total CPU has been divided into two parts. One is bus interface unit and another one is execution unit. The total CPU, in fact, is divided into two different parts. One is bus interface unit and one more is execution unit. This bus interface unit is used to communicate with the main memory because for the program execution, instructions must be fetched from the main memory. So there has to be a unit which will always communicate with the main memory. Whereas the other unit executes the instructions that are fetched from the memory. This is in a nutshell about these two units. Let us get into the details of these two units. This bus interface unit comprises of three major elements. One is the system bus, which comprises of address bus and data bus. Second one is a few registers. We talk about these registers and understand the purpose of the registers in some time. And in addition to these two elements, I do have another element which is called an instruction queue. An instruction queue can accommodate more than one instruction at a time. What is this? Let us understand. Every time when you execute an instruction, the concurrent instruction that is being executed should be fetched and stored within the CPU, right? Every processor fetches the current instruction that is being executed. Let us say currently the processor is executing 23rd instruction. So in order to execute 23rd instruction, the 23rd instruction should be brought into the processor and stored within the processor for the execution. Every processor does that. But when it comes to the 8086, the 8086 provides you an additional mechanism of storing a few more other instructions in addition to the concurrent instruction, the current instruction. That is, in addition to fetching the 23rd instruction, the 24th and 25th and 26th instructions can also be fetched. That is, not only the current instruction, also several other instructions that can be executed later in the course of the program, right after the current instruction, can also be fetched and stored in the instruction queue. This instruction queue is of 6 bytes, can accommodate 3 instructions. Why? Because one word in the main memory is equal to 16-bit. Nevertheless, moreover, 8086 is a 16-bit processor. So obviously, one instruction size is equal to 16-bit. Hence, our instruction queue, which is made up of 6 bytes, is going to accommodate 3 instructions at a time, not only a single instruction. This is the advantage of 8086. This is also called pipelining. More about pipelining we will discuss in the chapter of pipelining, but this is the starting point of the pipelining. Rather than fetching the currently executing element, we also get more elements than the current element. That is the actual starting point of the pipeline. In this case, the instructions that are fetched more than that of the instruction that can get executed within the CPU. Only one instruction can get executed within the CPU. But in addition to that current instruction, we also do get some more instructions. Here, the time will be saved. How the time is going to be saved? Right after the 23rd instruction, we need to go back to the main memory and fetch the 24th instruction. After 24th instruction, again we need to fetch the 25th instruction. This memory access consumes some significant time. So in order to avoid it, whenever we go to the memory for an instruction, rather than fetching instructions, 3 instructions at a time if we can fetch, that saves a lot of time. I hope you understand it. Yeah. Let us have a look at the execution unit. In the execution unit, of course, ALU will be the vital part. The ALU is going to be supported by some local registers. Of course, every ALU, no matter in which architecture you are in, every ALU should be supported with some local registers. What are those local registers? Let us say you are going to perform A plus B. A is an operand and B is an operand. In order to perform A plus B, these values of A and B should get transferred to the local registers of ALU for performing the operation. So every processor does support the ALU with some local registers, namely S and T. S and T are the standard and general names of the local register to any ALU. Take I3, I5, or take whatever. Local register names will always be, most of the times, S and T. And you can also see a flag register here. This flag register is going to hold a few flags. More about the flag register, we will talk in the flag register slide. But initially understand, every time when an instruction gets executed, the instruction is going to provide you some status bits, rather some status of that specific instruction. The output of an instruction can be positive, negative, or it has a carry, or it can be overflow. All these conditions will be depicted in their respective status bits. There is a sign flag. Sign flag holds the sign of the output. If it is 1, it is positive. If it is 0, it is negative. Carry flag will be equal to 1 if there is an end carry. That is, every time when you perform an operation, if the result has a carry, if the result produces a carry, then carry flag will be set to 1. What is the overflow flag? The overflow flag will be set to 1 if the output contains a wrong sign. That is, when two positive numbers are added, result should also be positive. If the sign is accidentally reversed, then overflow flag will be equal to 1. So the flag register is going to hold several status conditions that are actually observed at the outcome of the current instruction's execution. We will understand more about the flag register when we talk about a flag register. And there are some general registers. These general registers supports the instruction execution, and all these general registers are going to store some values which are fetched from the main memory. What kind of values that are going to be stored in these general registers, we will see in the next slide. Now, let us have a look at the address bus. 8086 supports 1 MB main memory. If it is 1 MB main memory, the number of address bits must be equal to 20, because 1 MB is equal to 2 power 20. So the address bus must be equal to 20 bit, but 8086 just supports 16-bit addresses. We will understand why 16-bit addresses. Now, dedicated address to generate 20-bit address. 20-bit address must be generated, but the address size address bus is always equal to 16-bit. There is a mismatch. Why? We will see. Now, just have a look at these registers. There are several registers: CS, DS, SS, ES, and IP. This IP already we know about it. What it is? This IP is all about the program counter. This program counter is renamed as an instruction pointer in 8086, which holds the address of the next instruction. Once again, IP is just nothing but a program counter which holds the address part of the next instruction. In order to understand CS, DS, SS, and ES, first we will understand main memory. Now have a look at this. This is the main memory of 8086. This is the main memory of 8086. You can clearly see the memory has been divided into 4 different segments. One is data segments, one is code segment, one is stack segment, and one more is extra segment. Each segment is of a size 64K. One segment size is equal to 64K, which is uniform for all the segments. And data segments starting address is 2000H. That is hexadecimal. That is, every segment will have a starting address. These registers, ES, CS, SS, and DS, are going to hold the starting address or the base address of that specific segment. For an example, when it comes to ES, ES is going to hold the starting address of extra segment. Extra segment starting address of the base address is 7000. Okay, so the ES is going to hold 7000. Okay, similarly CS is going to hold the code segment's starting address. Stack segment starting address is 5000, whereas stack segment is here 5000. Similarly, data segment starting address is 2000, which is going to be held. Now I just want to add something more to it. These registers are of 16-bit. These registers are of just 16-bit, but one main memory address is 20-bit. So these 16-bit registers are going to hold most significant 16 bits of the starting address. Actually, the starting address of this data segment is 2 0 0 0 0. This is the starting address. Altogether, it's a 20-bit. As we are representing in hexa, it is just of 5 digits, right? The equivalent 20-digit same 5-digit hexa has an equivalent 20-digit address, but the segment registers are of only 16-bit in size. So what these are going to do is, these are going to hold the most significant 16-bit of the starting address. It doesn't hold because it is not capable. So why these registers are used? How these registers are used? For an example, let us say this 2000H is, let us say 200 for time being. We will understand, we'll consider that the data segment starting address is 200 for an instance. Now a programmer wants to access the 23rd address within the data segment. Actually, the 23rd address is some different address in the main memory. When he directly accesses 23 will access some different location in the main memory, because 23 address is associated to some different location in the main memory. Now the programmer wants to access actually the 23rd location, the 23rd address of the data segment within the data segment. So every time when an address has to be accessed out of one segment, the base address of that specific segment will get added to the offset, the desired address. So 200 plus 23, which is actually the 223, the desired address required by the programmer, that is the 23rd address within the data segment, will be accessed when you add the starting address of this 200, starting address of the data segment, that is 200, gets added to 23, total 223. Thereby you will be able to access 23rd location within the data segment. This is the reason why we are going to use these segment registers, and these segment registers are going to hold the starting address, and that too only the first 16 bits, most significant 16 bits of that starting address, or the base address, whatever you call. Here it is given 8086 1 megabyte memory is divided into segments of up to 64 kilobytes each. 8086 can directly address 4 segments at a particular time. Program obtain access to code and data within the segments by changing the segment register contents to point the desired segment. As I already told you, 200 must be added to the desired address within the segment. When we club them both, we will get the actual result, the actual address that can be accessed, right? Once again, now let us have a look at what kind of a data that is going to be stored in these different segments. Data segment is going to hold the operands of a program. When a program is getting executed, it has 2 sections. One is code section, that is called the instruction section, and one more is data section, that is called the operand section. The code section of a program will get transferred to the code segment. The data section of a program which contains the operands of that specific program will get transferred to the data segment. And the stack segment is going to hold the return addresses. What is the return address? When one function calls another function, the current function return address must be stored in order to return from F2 to F1. F1 calls F2. But before I call to F2, F1's program counter value must be saved, unless there is no way I can come back from F2 to F1. So F1's return address will get stored into the stack segment. And stack segment also stores the local variables of a program. Extra segment. Sometimes it is desired to have an extra segment because every program requires some dynamic variables to be initialized. Dynamic variables are created by the runtime environment of a program. During the runtime, the program is going to generate some dynamic variables. All those variables will directly get transferred to the extra segment. This is what all about the type of the data elements that are going to be stored within the each element, each segment rather. Okay. Now Code segment register is 16 bits. Code segment contain the base or the start of the current code segment. Okay, that's it. Nothing else more about the code segment. Let us have a read. CS contains the base or starting of the current code segment. IP contains the distance or offset from this address to the next instruction byte to be fetched. I already told you 200 to be added to 23. This 23 is the current instruction that is needed to be accessed in the code section. Okay, that means the base address must be added to 23 in order to access 223rd instruction. Okay, BIU computes the 20-bit physical address by logically shifting the contents of CS 4 bits to the left and then adding 16 bits contents of IP. I already told you that this is only going to hold 16 bits of any address. The total address is 20 bits. Okay. Finally, a 20-bit address is going to be generated. Let us understand carefully. Finally, a 20-bit address is going to be generated logically to the left, and then we add instruction pointer. Then total 20 bits gets generated, right? Initially, the code segment holds 16 bit, but these are most significant 16 bits, right? So whenever we are adding the instruction pointer to this, these contents will be shifted left, and then instruction pointer will get added to this, after which total 20 bits will get generated. Okay, so that is all the instructions of a program are relative to the contents of the CS register. Unless you add the value of the instruction pointer to the CS register, you can't get it. You can't get the desired instruction. Data segment register, as you can clearly see, points to the current data segment. Operands for most instructions are fetched from this segment. Stack segment register, of course, the stack segment is going to hold the return addresses as well as the local variables. Okay, and there are two operations on the stack. One is push and one more is pop. There is something called stack pointer. The stack pointer always shows the top of the stack. That is, topmost element address will be stored within the stack pointer. Okay, there is something called base pointer. What is this base pointer? Try to understand. Now let us say F1 calls F2. F2 calls F3. When F1 calls F2, F1's return address will be stored into the stack. Let us say F1's return address is 23. At 22nd instruction, F1 makes a call to F2. F1's return address is 22. And you also know that stack also stores the local variables. What is the local variable? Local variable to a specific function. Now, F2's local variables will be pushed into the stack. Okay. Let us say it has a few variables. L, 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 L1, L1, L1. Local variables of F2 are stored right after F1's return address. Okay, now F2 calls F3. Okay. When F2 calls F3, F2's return address will get stored into the stack. That is, let us say 34. After which F3's local variables will get stored, right? That is L2, L2 local variables 2, local variables of the function 2, again local variables of the function 2. Let us understand carefully. Here in our stack, there are two different segments. One is this segment, okay? In this segment, it corresponds to F1's return address and F2's local variables. Here, it corresponds to F2's return address and F3's local variable, right? Now the base pointer is going to hold the base of the each function. Let us say whenever a function call has been made, the base pointer is going to hold the address from which the call has been made. This 22, which is the return address of the previous function. In addition to this, local variables of the calling function, the called function has been stored, right? This is the return address of the previous function. These are local variables of the current function. So this will be a set which is going to be depicted by the base pointer. When this function calls another function, this base pointer gets updated to this place exactly. Because in this segment, the calling function's return address and the called function's local variables. So every time base pointer is going to specify the base address of the current function. In this segment, in this specific segment of a stack, we do have two things. One is the return address of the previous function and the local variables of the current function. Every time base pointer gets updated when a function calls another function. This is the difference between stack pointer and a base pointer. Extra segment register points to the extra segment in which the data in excess of 64K point in the data segment is stored. Yeah, as I told you, extra segment is going to hold the dynamic variables. But sometimes when the data segment is not sufficient, the data elements can also be pushed into the extra segment. This is the thing. Instruction pointer, nothing more to talk about the instruction point. It's a 16-bit register which is going to hold the address part of the next instruction. Yeah, it is just showcasing the discussion what we had earlier in the session. This is the instruction queue which is of 6 bytes. A group of first in first out FIFO in which up to 6 bytes of the instruction code are prefetched from the memory ahead of time. This instruction queue, this queue, of course, the queue strategy is first in first out. The first fetched instruction is going to be first out instruction that is executed, that is going to be executed. This is done in order to speed up the execution by overlapping the instruction fetch with the execution. Rather than fetching a single instruction, every time when we go to the memory for an instruction, if we are able to fetch more instruction, isn't that speeding up the operations? Absolutely. It speeds up the total performance. Because let us understand something very carefully. Every time when you go to the memory involves in a latency. When you access something out of a processor register, it will be very faster. When you access the same content out of the main memory, of course, it is proven to be very slower. Memory access is very slower comparing to a register access. So what we do is, rather than fetching only one instruction at a time, we'll get more instruction at a time. Every time when we go to the memory for an instruction, you get more instruction, as many as possible, as many as are supported by the instruction queue. Then the computation gets speeded up. This is the mechanism that is called pipelining, as we already discussed. Execution unit, as I already told you, decodes and executes the instruction. This decoding will be done by the control unit. The control unit will be attached to a decoder which decodes the opcode of the instruction. 16-bit ALU for performing arithmetical logic operation. And the system also supports 4 general purpose registers AX, BX, CX, and DX. We'll understand these registers in the next slide. In addition to these segment registers, we also do have some general purpose registers AH, AL, AX, BX, CX, and DX. Okay. In addition to this, we do have stack pointer and base pointer. I talked about stack pointer and base pointer already. And index register, there is something called source index and there is called destination index. Okay. And yeah, these 16-bit registers, AX can be divided into 2 different parts. One is lower byte, higher byte. AX is a total register. AX is a label for this total A register, in which there are 2 bytes, lower byte, higher byte. Similarly, BX is the name of the total register, in which there are 2 bytes, lower byte, higher byte. Similarly, each and every register is of 2 bytes. One is lower byte and higher byte, and which is denoted by a specific register's label followed by X. When you have a suffix X, then it says that it's a label of the entire register. Accumulator register. Let us start talking about an accumulator register. It consists of 2 8-bit registers AL and AH, as I already told you, which can be combined together and used as a 16-bit register. AL in this case contains the lower order byte of the word and AH contains a higher ordered byte. The IO instructions use the AH or AL for inputting outputting 16 or 8-bit data to or from the IO port. Let us understand that from a keyboard, a character has been typed. This typed character will directly be transferred to either total AX or AL. But I don't need the complete register, because when you input a character, the character size will just be 8 bits, because you always deal with the ASCII characters. When you use a peripheral device, the peripheral device is going to work based on an ASCII format. The ASCII format characters are just 8-bit, or of 8 bits in size. When you feed the system an ASCII character, it is of just 8-bit size, will directly get transferred to AL, that is the lower byte of the accumulator. And the multiplication and division instruction also use the AX or AL. Of course, when you perform arithmetic multiplication or arithmetic division, for the results, we are going to use AX. Second one is the base register. Consists of two 8-bit registers, BL and BH, needless to discuss, which can be combined together and used as a 16-bit register BX. BL in this case, lower byte, BH in this case, higher byte. This is the only general purpose register whose contents can be used for addressing 8086 memory. Let us understand what is the purpose of a base register. Every time when a program is stored, this program will have a starting address. Similar to every segment has a starting address, every program also has a starting address. The starting address of any program will get stored into the base register. Let us say the computer is dealing with X program. X program is available at right from 250th location. Okay, now this 250th address will get stored in the base register. Now, when you want to access an address within the program, you need to access it in relation to the base register. Okay, all the memory references utilizing this register contents for the addressing use data segments as the default segment register. Of course, for a program, data will be available in the data segment. So for this, any program, data segment will be the default segment register. Counter register CX, which is going to be initialized by the loop count. Every time when you perform a loop within your program, there will be a count initiated, right? That loop count will get transferred to the counter register. Okay, that consists of course, to 8-bit CL and CH, and finally CX is the total label. When combined, CL register contains lower ordered byte of the word and CH contains higher ordered byte. Instructions such as shift, rotate, loop use the contents of CX as a counter. How many times the loop has to get rotated? Defined by the counter register. I is equal to 0, I less than or equal to 100. Then the counter register is equal to 100. For every iteration, this gets decremented. The moment it gets 0, then the loop gets terminated. You can look at the example. The instruction loop start automatically decrements CX by 1 without affecting flags. We'll check if CX is equal to 0 every time when a decrement happens. If it is 0, 8086 executes the next instruction. Otherwise, 8086 branches to the label start. That's it. That is, if it is 0, after the loop, next instruction will get executed. Otherwise, it will go to the starting point of the loop. Data register. This data register purpose you need to understand very carefully. When a multiplication operation is performed, the data register is going to hold the 16-bit result. But the multiplication can be in between 216 and 216. Right? Here, this data register is going to hold the high 16 bits. High 16-bit result in addition to the accumulator. Already accumulator is holding some output value, right? Whenever A into B is performed, where A is equal to 16 bits and B is also equal to 16 bits, the resultant C may be more than 16 bits, may be equal to 32 bits, let us say. But there is not enough room within either data register or accumulator. At that time, data register is going to hold most significant bits, 16 bits in the result, and the accumulator is going to hold least significant 16 bits in the result. Similarly, when a division is performed, the 16-bit dividend, it is going to hold, the data register is going to hold the 16 bits dividend. After the complete division, it is going to hold a remainder. Once again, this data register is going to hold the dividend initially before the division is performed. Right after the division is performed, this data register is going to hold the remainder. Stack pointer and the base pointer. I told you already what is the stack pointer and base pointer. Stack pointer is going to hold the topmost element's address of the stack, and base pointer is going to hold a specific function when it is called. a specific function segment within the stack. Source index and destination index. Used in indexed addressing, we will see what it is in the addressing modes. During the addressing modes, I'll explain you what is a source index and destination index register. About a flag register, we will discuss in the next session. Thank you.